In this lesson, we'll take a further look at the voltage controlled current source that we have designed and also understand some terminology that is commonly encountered and so on. Okay. Now, our voltage controlled current source using a single MOS transistor is made like this. We bias it with a current source in the source, and the most commonly used way of biasing the drain is through a bias resistor RD, and we AC couple the load to it, and we couple the resistor which defines the transconductance R1, and we also AC couple the input. Okay. Now, the quantity that is controlled by feedback is the small signal incremental current in the drain. Okay. And I naught by Vi is approximately 1 by R1 if Gm R1 is much more than 1. Okay. And in this particular circuit, this I naught divides between RD and RL in inverse ratio of their values. Okay. So the current that flows here is really I naught times RD by RD plus RL. Now it so turns out that a lot of times, although this is a voltage controlled current source, it is used with a voltage output. Okay, you measure the output voltage instead of the current, and that's very easy to do. Okay, what is this output voltage after all? If I define this to be V naught, V naught will be equal to minus I naught RD by RD plus RL times RL. Basically, this I naught is going through a parallel combination of RD and RL, and because of its polarity, we get a negative sign. Okay, and if I expand this out, I will get minus the exact value of I naught, by the way, is Gm by 1 plus Gm RL times Vi, and this quantity of course is RD parallel RL. Okay, so that will be the output voltage, and when this condition is satisfied, when Gm R1 is much more than 1, this is approximately minus Vi times RD parallel RL divided by R1. Okay, so the gain, the voltage gain, if you think of it that way, is defined by a ratio of resistors, and that can be defined accurately. That is more accurately than defining the transconductance of a MOS transistor, which varies significantly with temperature and so on. Okay, especially on an IC, the ratio of resistors can be quite accurately fixed. Although I consider the output voltage, this is not a voltage controlled voltage source. Okay, this is a voltage controlled current source with a load resistor. How do you differentiate between the two? If it were really a voltage controlled voltage source, then changing the value of the load resistance or connecting another resistance in parallel with this shouldn't change the output voltage at all. Whereas in this case, it definitely changes the output voltage. Okay, this I naught is fixed. That is independent of what load you connect. So the voltage V naught will very much depend on the load resistance that you connect. So this is really a voltage controlled voltage source with a resistive load, and it is used like this, and sometimes we won't discuss it, but this I naught is passed through some resonant circuit to form a resonating amplifier and so on, a tuned amplifier which is used in many RF circuits. Okay, we won't discuss those things, but this voltage controlled current source can be used with a variety of loads to give you different kinds of functions. Okay, now this circuit you see is very similar to, let me copy this over. I have copied over the same circuit, and what I want to highlight here is the similarity to a common source amplifier with source feedback biasing. Okay, now let me go back to that circuit. Common source amplifier with source feedback bias. What did we have in that case? The only difference between this and that circuit was this R1 was not there, it was short circuited, and C3 was connected directly to ground. You choose C3 such that its reactance is much smaller than 1 by Gm. In other words, C3 is much greater than Gm by omega, where omega is the signal frequency. Now we know the results for this case. This is also a voltage controlled current source. Okay, let me call this I0 prime. What is the small signal equivalent after all? It is the input source, and let me assume the capacitor to be a short circuit. We have R1 parallel R2, and we have the transistor with its source grounded. Okay, this is the way we use the transistor amplifier. We have VGS, and Gm VGS is the incremental drain current. Okay, so this I0 prime is nothing but Gm VGS. Okay, and that goes into a parallel combination of RD and RL. Okay, now if you look at the output voltage here, V0, we know what it is. We have calculated it so many times. It's minus Gm RD parallel RL times the input voltage Vi. Okay, so this is the common source amplifier, and this is a voltage controlled current source with a resistive load. In fact, this is also a voltage controlled current source with a resistive load, where the voltage controlled current source is just the MOS transistor by itself. Okay, this is also a voltage controlled current source. Okay, the only difference between these two is that in this case the ratio of output current to input voltage is defined by the MOS Gm, whereas here if you choose Gm R1 to be much more than 1, the ratio of output current to the input voltage is defined by this resistor R1. Okay, so they are very similar in functionality, and for that reason many times this particular amplifier is also called common source amplifier with source degeneration. Okay, degeneration means something is degenerated or reduced, and in this case what is reduced is the transconductance. Okay, in this case I0 by Vi is Gm by 1 plus Gm R1, which is approximately 1 by R1, and this is definitely going to be smaller than the Gm of the MOS transistor. Okay, in fact you choose this Gm R1 to be quite large, so this number here is going to be quite a bit smaller than Gm, which is just the transconductance of the MOS transistor. Okay, whereas this is the original common source amplifier. Okay, so it is said that the Gm of the transistor is degenerated by placing a resistance in series with the source. Okay, and this becomes clearer if we draw just the small signal picture. I'll omit the bias resistors R1 and R2 for simplicity, and I'll also assume that all capacitors are short circuits. A voltage controlled current source with a resistive load. This is used with a voltage output, as I mentioned. It looks like this. This is Gm and this quantity is VGS. Okay, these are the drain, gate and source terminals of the MOS transistor. And the common source amplifier, it's very similar, of course. Except that the resistance is not there and the source is connected to ground. Okay, so if I call this I0 here and there, I0 by Vi here is Gm by 1 plus Gm R1, which approximates 1 by R1 if Gm R1 is much more than 1, and in this case I0 by Vi equals GM. Okay. So this has a smaller transconductance I0 by Vi, and it is referred to as degenerating the transistor. By connecting a resistance between the source terminal and ground, what happens is the effective gate source voltage here is smaller than Vi, whereas the gate source voltage here is exactly equal to Vi. So the transconductance is reduced. But why would we do this? Why do we reduce the transconductance? First of all, it becomes independent of this GM, which has some desirable properties because GM is very sensitive to temperature and so on. And another aspect which we have not discussed so far is that this circuit is more linear compared to this one. Okay, that is, you can apply a larger signal, larger value of Vi to this without driving the MOS transistor into very severe nonlinearity compared to this circuit. Okay, that's another feature of negative feedback. Of course, I have only stated it vaguely because to specify it exactly, you have to also make quantitative comparisons. The transconductance here is smaller than this and so on. But in general, this circuit is more linear than that, and this is used for that purpose. This is degenerating the transistor. Okay, and this resistor is sometimes called the degeneration resistance. Okay, and instead of the output current, you look at the output voltage VO like this. Then we'll have V0 by Vi to be approximately minus RD parallel RL by R1 in this case, again under the same condition that GM-R1 is much more than 1, and V0 by Vi is minus GM RD parallel RL in this case. Okay, so many times you see this terminology, the degenerated MOS amplifier, and this is what it means. If you have a resistance in the source, then you can think of this entire block, these three terminals, this and this one, as a three-terminal element whose GM is much smaller than that of the MOS transistor by itself. Okay, so that's what degeneration means, and this circuit is also a very widely used basic building block. Okay.